maybe if I start a little bit about sort of the motivation around why I was thinking about this particular talk. So I suppose I've been working in data science and machine learning for probably 10 years at this stage. When I started out, I was kind of very excited. You know, I learned about Pandas, and then I built some models in scikit-learn. And then I kind of I came to a project where I was working with text or unstructured data, and I tried to follow the same sort of workflow pattern. And I kind of realized quite quickly that actually Pandas doesn't scale that well. It's quite memory intensive. I didn't know that Pandas isn't very good at handling string data or text data. And I also did some silly things, you know, like getting a sparse matrix and exploding it for whatever reason or something like this, and just everything kind of just stopped working on my machine and all this kind of stuff. And then sort of, I suppose, this kind of sort of big data tools came along, like PySpark, and I was like, okay, this is great, I'll try and give these a go. And I suppose my experience with PySpark and Scala and all those kind of stuff is this kind of a steep learning curve in terms of trying to go from my single machine up to a shared cluster resource, trying to spin up clusters, then I have to contact people, and this is my own internal organization, obviously cloud is different. And then I end up messing up something with the data, and then I have to go into sort of trying to debug and trying to understand what happens. And for me, for my workflow, it's never really sufficient. It kind of breaks how my thought process goes. And I end up going back and sort of sampling data and then kind of doing stuff back in Pandas. And then you kind of run into sort of part of the problem of how do I take something that I've built there and then scale it up for production or whatever into a system. So more recently, there's kind of been sort of a change in some of the tooling that is starting to maybe start to bridge that gap so that you can stay in the same tool for longer, for bigger data, and then that interoperability to move from your local working machine up to production environment or scaled environment more seamlessly. And that's kind of what the intent of this talk is. So my name is Brian Carter. I'm Director of Machine Learning at Optum. Optum are a healthcare company in the States. They're in every vertical of healthcare that you could imagine. And for this talk, I really want to talk through some libraries from the consumer point of view, not from a developer point of view. So I'll just put that out there in case somebody asks me a very tough question at the end. So some of the tools that I'm going to quickly touch upon. So Pandas, everyone knows about. DATA.TABLE, MODIN on Ray, which is coming from the RiseLab in Berkely. This kind of interesting library called VAEX. And then with time allowed, I'll try and do some live-ish demo or something. We'll see how we get on. So I kind of alluded to earlier, my day-to-day job is really analysing data. Well, sometimes it's getting data and negotiating what the problem is stuff. But once I get the data, I'm kind of like it's doing the analysis on the data. And I really don't want to have the mental burden of switching between different toolings or different APIs as I move across different compute platforms. And I do, as I said, I often find times moving from a single machine technology to a big compute does kind of enforce that on me, and it kind of breaks that thought process. So before kind of sort of dive into some of those libraries, I think it's kind of worthwhile thinking a little bit about why Pandas is so popular. The Pandas API has is a very rich and powerful API. There's over 300 methods in Pandas. And really, it's this ability to construct SQL-like actions without having to get into the verbosity of SQL or the illegibility of sort of some of the SQL nestings. And you can run a line of code and you get your results straight away. And that interactivity or literate programming paradigm is quite powerful. Sort of the literate programming the aim is to develop programs along with the logical flow of your mental thought process. And it surprises me sometimes when I sort of start talking with software engineers, and that point is sometimes, like, it's very hard for somebody to really understand that unless they've worked with data and they've kind of gone through that whole process of sometimes it's called data munging or data debugging, but it's really kind of understanding what are the systems that generate your data, and that kind of back and forth and kind of investigation. And so within that kind of recognising that powerful paradigm of pandas, this talk, I mean, the stuff I haven't finished here is I really kind of want to think about these libraries in that context, in terms of the usability context, before kind of getting into, say, more traditional benchmarks and sort of thing. So just before kind of jumping into the libraries, and I'm sure probably a lot of people know this sort of stuff around the underlying sort of change towards column-orientated storage or formats, disk formats and memory formats. So we all have this kind of logical representation of what data looks like in terms of this table representation. However, on a disk, and that's kind of this 2D representation on the left-hand side, but on a disk, it's 1D or linear. And the row is the traditional method of storing data. And this works really well for writing in a traditional relational database sense. But it's not great for pulling large amounts of data, and especially like when we think about stuff around filters, there's a lot of overhead with disk seeks in terms of pulling data off the disk into memory. And then the benefits of having a columnar data structure is that we group similar data together, so it's homogeneous data types. You can encode that data and then you can compress that data. And also then for when we're doing reads where we have a filter, we can pull one column, where you've got a where statement, find all the indexes and then use that to pull all the rest of the data. So it's a much more efficient way of storing data. So on the left here is kind of represents that each system has its own internal memory format. There's a lot of wasted time on serialization and deserialization. There's a lot of wasted time on conversions. On the right-hand side is a standard memory format, Arrow, and this allows for cross-system communication. And the Arrow API essentially breaks down the silos between different libraries and different languages. So, you can have Java can read from Arrow, C++, Python, or and they can all talk to each other. It kind of breaks down sort of, I'm working on this tool, you're working on this tool type stuff. It allows for embeddable, so you can share functionality. So we can have a Parquet, which is the on-disk column-orientated storage format. So you can have a Parquet to Arrow reader that can be shared across languages, and it's interoperable. So the goal or the long-term vision then is that you can actually move between different systems without actually having to change too much stuff. So Parquet, as I said, is the disk column-orientated storage format from Apache. It's developed for input-output priority. It can have nested data structures, and Arrow is the in-memory column format, and it's optimized for CPUs with nice stuff around pipelining and caching. So sort of the first first library I want to talk about is DATA.TABLE. So DATA.TABLE was created in 2006 by Matt Dowell, and he's currently at H2O. And its initial focus on time series and genomics. And recently H2O has ported this to Python, and they say they can get up to 100 gigabytes on a single node machine. The reason I kind of wanted to talk about this was because back a couple of years ago, I used DATA.TABLE in OR, and actually it's quite powerful, but it sort of required me to learn a new API and a new syntax, and the syntax actually is quite readable, and it's very short and it's concise. It has this matrix, you have your rows I, your columns J, and then you can do the expressions which are group bys. But it did sort of enforce that requirement on me to learn a new syntax, and I found then when I was working with other people, then bringing that code to them, then that enforces them because they haven't used it and that kind of sort of thing. So sort of in this evaluation, which I get to kind of towards the end of the talk, is so DATA.TABLE is now available on Python. It's column-orientated data structure. It's got native C implementation for all data types, including strings, which is different to to Pandas, which only really has that for NumPy through numeric columns. It's got support for datetime and categoricals, and eventually it's going to have memory mapping in it. That said, sort of in my experience of DATA.TABLE in Python, is the API is at the moment is quite limited. It doesn't have a huge range, so yeah, it's kind of one to watch anyway. But I kind of get onto that as well. The second library I come on to talk about is MODIN on Ray. And before I kind of talk about MODIN, I just want to talk a little bit about Ray. So Ray is a system and architecture from created in the RiseLab lab in Berkely, who kind of, I suppose they're the guys who brought Spark at one stage. And so its attempt is, so in a typical machine learning workflow, you have all these different components. You have your training, your serving, streaming. You can have distributed reinforcement learning for agent type stuff, data processing, hyperparameter tuning. And there's a whole ecosystem of tooling available for that. And even when you talk to companies, you see this in a lot of companies, they end up having to build their own platforms for all these systems to talk to each other. And Ray is an attempt to create a unified system to support all these different components of an ML workflow. Yeah, so I'm not going to go too much into Ray, but I just kind of want to highlight that MODIN is one part. So Ray is not just the systems and architecture, they're also building libraries on top of Ray. And MODIN is one of those libraries for data processing, which is the Pandas on Ray or whatever. So MODIN has this tagline of accelerating your Pandas workloads by changing one line of code. And that's kind of what I also tried to test out here. So they essentially have this, that you can just import modin.pandas as PD. That's the same as you import pandas.pd. And your code will work exactly the same. And so their claim is also that they'll allow you to move seamlessly between megabyte analysis to terabyte analysis. It automatically uses all the cores in your machine, so unlike when you're using Pandas, it'll be single core. Unless you configure it, otherwise MODIN will just grab all your cores for reading it in your data. In terms of coverage, so they have 80% of the Pandas API covered at the moment, so it'll be completely seamless. If you can just change that line of code, and if it's something that it doesn't have in Pandas, in the background, it'll just convert the data to Pandas data frame, do the operation, then convert it back to the Ray object storage, which is kind of one of the things that's underlying it. And then the last library that I kind of want to touch on is this library called VAEX, or VAEX. So VAEX was a visualization library, and it's now a data frame library. It's out of core data frames. It has this concept of data and state, which I'll talk to in a minute. It can read 1 billion rows in a second on a single machine, which I'll hopefully demo to you guys. And it's optimized for string processing, so there's up to 1,000 times improvement on string processing with respect to Pandas. Again, it's column storage. It has this HDF5 storage format, which isn't overly common. It's very memory efficient, and it also has been, as its origin was in a visualization library, it has some nice visualization stuff, and it has some ML stuff built in around. It's got light GBM, I think, is incorporated in it. So just quickly to kind of talk a little bit about what that VAEX data and state looks like. So in terms of, if we were doing this filter on the top row where, we were looking for the column C, less than 0, and then trying to do a sum in it, in the background Pandas would create a separate data frame to do that, compute the result, then delete that data frame, send it back to you, which is a little bit, which actually is very memory intensive. In terms of the way VAEX would do it, it has this concept of a dictionary state. So it doesn't make a copy of the data, it just creates a dictionary saying the original data was the DF, and then it creates this state with the filter, and then it has a lazy expression it'll compute when you want it to or when you need it for. This has some added benefits as well, because if you think about all the operations that you might apply to a data frame as part of a data pre-processing to go into your machine learning model, this dictionary, you can save the state, and it's essentially your pipeline then that you can apply to your new data as it's coming in. It also has this concept of a virtual column. So if you add a column, again, it doesn't make a copy of the data. It just creates the state saying saying what the virtual column is in this state dictionary, and then does the computation on that when you need it. So that's kind of the 3 or 4 libraries that I'm going to talk about today. I kind of started out a bit more ambitious on this talk in terms of how much work I get done, but like, I mean, there's a good few more libraries out there that I haven't covered on, that I hope to sort of keep building this up in terms of SFrame, which I think is Apple maybe developing this at the moment, Dask, PySpark, and then there's CUDA data frames with Rapids, and then X-frame, the C++ data frame library. I need to kind of work a little bit on what my evaluation set was and refine some of the benchmarking and stuff. So in terms of, like, I mean, as I said at the top of the talk, I really kind of wanted to start off focusing in on what for me I think is sometimes the most important thing is the interactivity and the interoperability between these libraries. So I've kind of started sort of putting this together, but probably the best thing is maybe if I kind of jump into to give some examples, if I can get this mouse working. So just to kind of give you an example, so I'm kind of using one of the New York City cab data sets. It's kind of, they put them out monthly. They're kind of used in lots of places now. And it's just 1 month, so I just kind of wanted to show about converting this data. So in terms of, and I'm not going to run this now, so like, I mean, Pandas doesn't do too bad a job. It's like, it's a 2.7 gigabytes, and I think it took like almost a minute to read it in. And then in Pandas at the moment, you're able to convert the CSV to a Parquet file. So the default compression is snappy, and that reduces the file from 2.7 gigabytes down to 2.7 gigabytes. Another compression is gzip, and this reduces it further. So this is taking the same CSV file and reducing it down. It gets to 0.5 gigabyte. Interestingly, I got a bit flummoxed in terms of Dask doesn't like this compression. It's snappy when you're reading Parquet files in with Dask. It only likes the gzip. I'm not 100% sure what the development plan is around that. HDFFs is this hierarchical data format. Again, it's kind of sort of more like a folder structure. You can append multiple data frames to it, so it doesn't compress as much. And then there's this HDFF5 created with VAEX or with VAEX. Yeah, so like the kind of what I wanted to point out is, like, I mean, it's still. I was kind of looking through, seeing if I can find a command line tool to do these compressions, which I haven't, but maybe it's something that I can work on so that we can kind of not have to use Pandas, you know, if the need arises. So for the HDFF5 conversion, I had to use the VAEX, and this reduces down to 2 gigabytes. So in terms of, like, I mean, what I kind of just wanted to quickly evaluate or kind of show here is I just kind of said, okay, what's kind of a set of things that I kind of like to do when I open up a file in Pandas. And so just to give you sort of an example, so this, you know, I created files, but like, I mean, it takes about a minute to read in that 2.7 gigabyte file when it's a CSV. When you jump to the Parquet file, the snappy one, just the default one, it takes about 3 seconds to load in, so it's a significant drop. The gzip one about 6 seconds, and the HDFF about 4 seconds. And then some of the operations that I kind of wanted to compare across these libraries is if I sort of do a summary or with the Pandas describe, how long that takes. So it takes about 10 seconds here. Can I do a quick value count? Can I do something with dates and do a group by and just compare what the API looks like for each of these in terms of working through that. So let me see, how am I on timer? 5 minutes, okay, wow. So maybe I'll just quickly jump to MODIN. So I just want to show the point. So essentially this MODIN file is exactly the same as this Pandas file. The only line difference is the change in this Pandas import MODIN as Pandas PD. Everything else works exactly the same as in Pandas. It's actually a little bit slower, and that's because it's got this partition, because if you partition up your data, there's an overhead in terms of all this communication back and forth between it. But I think if you scale up, that idea that you could move this onto a clustered environment without changing anything is quite powerful. And then maybe I kind of jump into VAEX, because VAEX is kind of interesting. It's a little bit different, but in terms of sort of speed, so yeah, maybe I'll just try and run this so we have a bit of a demo. So I don't want to do it with that. So let's do it with the HDF5. So this is in terms of loading in this file, which is 14 million rows of data. This is with VAEX. So that's it done in 95 milliseconds. So it's got the 14 million rows in there. I think it takes, I don't know how long it takes now for the 4 seconds to do the describe. This is the virtual express, or the state where you've created these expressions. So it hasn't actually calculated anything, this stuff at this point, and it just shows you the top and bottom. If you want to do something around calculating the percentage, so still quite powerful in terms of like 93 milliseconds for calculating the mean on 14 million rows. And that's doing the value count. I think I did some stuff with group by down here. And what maybe I kind of jumped towards the end, and you can kind of see this on the Ortimer, I think he's a few videos up around this kind of stuff is. So, where am I? Let me see. So this file has 1 billion rows in it, and so I'm going to read it in on this machine. So I've read in 1 billion rows into the data frame. Then I can run the value counts on it. Probably takes about 10 seconds. So not bad in terms of doing 1 billion for 1 billion rows calculation. And kind of one of the kind of nifty little things I kind of like about it is, so the data set well, it's kind of a little bit idiosyncratic in it, but the data set was a visualization library. So this here I've just plotted the latitude and longitude on this data set, and it's the New York taxi trip data set. So there's a little dot in there, and I don't know if I'm going to be able to do this, but we'll see. So I can zoom in, because you can see that the latitude and longitudes are way off in terms of what you'd expect a latitude and longitude range. This mightn't work. Oh. I don't know, is this going too well? This is going back to the data all the time and stream the data through the filtering. And there you can kind of start to see the outline of New York City in terms of, so the ability then to, when you're kind of working with that type of data, to kind of like conceptually say, okay, if there's wrong values in there and that kind of stuff is quite powerful. So that's my talk. Thank you very much, everyone, for listening.